All right, welcome back after this short break to the next talk by Jarl Flaten, also from University of Western Ontario. And Jarl will give a talk on the X groups in homotopy type theory.
Thank you, Benedict, and thanks to the organizers for this opportunity to speak about X groups in homotopy type theory. This is joint work with Dan, who you just saw speak, and yeah. My outline is as follows. I will begin by defining X in homotopy type theory. And for that, let R be a ring throughout. And so I'll define X1 over a ring R. And as you should always do when you define a new type, I will characterize the paths in X1. We'll see that the trivial extensions are the merely split extensions. And this leads us to a notion of projective modules in homotopy type theory, which are the merely projective modules. And I'll explain that as we go. And sort of up to here, things will seem very familiar to you from the classical setting. But I'll explain that this last part is surprising. And in fact, X1 is equivalent to a small type. Then I'll pass to an infinity topos, which by work of Schulman, we know is a model of homotopy type theory. And I'll discuss the important notions of internal projectivity and injectivity in these models. And we'll see that we recover something classical called sheaf X, which has kind of been studied by algebraic geometers previously. And I'll leave you with an example of a non-trivial X2 over the integers in the Sierpinski topos. So this is something that looks very non-classical. OK. Before defining X in homotopy type theory, I want to give you the classical analog, which is the motivation for our definition. And this is the Yoneda X, which is available in any abelian category. So for this, let curly A be an abelian category and pick two objects, A and B. Then you can define X1 as follows. It's pi naught of a groupoid of short exact sequences, where pi naught is isomorphism classes, if you think of this as a category. So more concretely, there is a category of short exact sequences whose objects are things like I've written here. And if I have another object, a f b, then a morphism between them is a map of short exact sequences, which is the identity on A and identity on B, and some phi in the middle here, making the diagram commute. So this phi is always an isomorphism by the phi lemma, and so this forms a groupoid, and we take pi naught of it. Now, I want you to notice that this produces large groups. We know examples where these X1s are proper classes, in fact. Moreover, this X group is external to the category A, by which I mean it is an abelian group. It is not an element of curly A anymore. In contrast, the X groups we're defining in HoTT, they will be internal. So I want you to keep these two things in mind as we continue. OK. So now we are in homotopy type theory, and we have a ring R. And we consider two R modules, A and B. And let me just remind you, these are in particular sets. They're not some sort of untruncated types. Then we define the type of short exact sequences from A to B as the following sigma type. We sigma over all R modules E with maps going in, maps going out, such that I is a mono, P is an epi, and we have exactness at E. It's a very sort of natural analogous thing to do with comparing to the previous slide. Now I want you to notice this definition here makes this type of short exact sequences into a large one type. And that's because this category of R modules is. More specifically, I'm sigmaing over a large one type, which is the base, and everything else here are small sets. And the innermost thing is a proposition. So this is sort of analogous to what we had on the previous slide. Moreover, we can easily characterize the paths, since we know well what paths are in sigma types. So if E and F are two short exact sequences, then paths between them correspond to paths in mod R, which are just R module isomorphisms. EF satisfying a certain transport condition, but this transport condition, so transport in families of maps is by pre and post composition of maps. So we end up with a condition being that phi make this diagram commute. So this tells us that this type of short exact sequences, this groupoid of short exact sequences, is analogous to the groupoid we had on the previous slide, and incites us to define the set of extensions x1 as pi naught of the type of short exact sequences. Now this becomes an abelian group under the Bayer sum. You can define that internally in HoTT, with the 0 being induced by the trivial split short exact sequence. So let's now see what are the trivial extensions, since we know paths of short exact sequences. And we'll see that the trivial extensions are the merely split ones. Now at the top here, I have the lemma from the previous slide, just written in symbols. And the proposition is as follows. Let AEB be a short exact sequence of R modules. Then when we consider this short exact sequence as an extension by set truncating it, then it is trivial if and only if the map P merely splits. By which I mean this proposition here holds, i.e. there merely exists a section of P. Now, the proof sort of follows the classical version. So as usual for the untruncated types, let me write it a bit nicely. And then you truncate to get the statement for x1. So there's nothing much interesting going on there. But this notion of P merely splitting is quite interesting. And I want to sketch the phenomena to you in a model. So consider curly E, the topos of G sets for a non-trivial group G. Then abelian group objects in E correspond to ZG modules over the group ring ZG. Now, there's a natural epimorphism going from the group ring itself down to Z with a trivial action. And it doesn't split. Doesn't split, yeah. And it's because there are no interesting maps going the other direction. These need to be equivariant. However, it does merely split. And the underlying reason for that is that there exist abelian sections. And as you might know, the internal Hom in this setting consists of abelian group maps from Z to ZG up to with a G action. So even though there are no global elements of this internal Hom, meaning no actual sections, there are partial elements, i.e. non-equivariant maps or non-equivariant sections. And this is the reason this map merely splits. I think that's an interesting observation that we'll come back to later. Now, having seen when extensions are trivial in HoTT, we come to the notion of projectivity. So let P be an R module, then the following are equivalents. All epimorphisms into P merely split. Secondly, for all F, like this, sorry, from P to B, sorry, yeah, and epimorphisms like this, there merely exists a lift. And so by the discussion on the previous slide, there might be some non-equivariant lift, despite there being no equivariant lifts. And lastly, this X1 group is 0 for all R modules A. And if any of these hold, we call P projective or merely projective if we want to stress that. So this proposition should seem quite familiar to you if you thought about R modules classically. And a lot goes through as in the classical case. In particular, we've defined Xn, so the higher X groups, and verified that you obtain the expected long exact sequences. And moreover, you can compute Xn in terms of injective or projective resolutions when they exist. I want you to keep in mind this proposition because we'll be using it in a model later on. What sort of where things differ from the classical case is that, in fact, X1 is equivalent to a small type. So we saw that Uneta X, which was external, was in general a proper class, but this sort of doesn't happen for internal X. So to see this, recall that we have an equivalence of categories for n greater than 2 between pointed n-1 connected n types and the category of abelian groups. This is a very classical result, and it was proven in type theory by Buchholz, Van Doorn, and Rieke in their higher groups paper. Now we have the following proposition, which is well known, but I'm stating it for our type of short exact sequences. And it says that this type is equivalent to the type of pointed maps from KBN into B-odd KAN. And let me remind you, this is the component of the universe of KAN. Now the proof is sort of nice and conceptual, so I'll briefly sketch it. If I start with a short exact sequence AEB, I can apply this equivalence of categories to get a fiber sequence as follows. And then any fiber sequence is classified by a map into the universe, which in this case lands in the component of the fiber. So we get a map on the right-hand side of the equivalence. Now to go from right to left, you include into the universe, and you pull back along the universal fibration. OK, so this proposition is not surprising. But let me remark that this B-odd here is a small type, or is equivalent to a small type, by the theorem of, so it's small, by the theorem of Rieke that Dan spoke about half an hour ago. And thus we obtain the corollary that X1 over the integers is equivalent to a small type by truncating this equivalence. But you can generalize that to any R. That's not too difficult. OK, so now I want to pass to a model and discuss what we obtain by interpreting these results into a model. So by model, I mean infinity topos. But since we're considering sets, we end up, in fact, over a site with a sheaf of rings R on this site C. So our X groups are interpreted as some objects, some sheaves on this site. I will use the same notation, even though I'm not in HoTT anymore. I'm now in a model. And in order to see that we obtain something familiar or something classical, I need the following definition. An R module I is externally injective if the external HOM sends monos to epis, and it is internally injective if the internal HOM sends monos to epis. And let me say here, this AB here, those are plain old abelian groups, whereas this mod Z are sheaves. So Z is a sheaf here over our site C. That's why it's internal. Now we have the following theorem due to Blechschmidt, saying that external injectives are internally injective. And it is well known that mod R has enough external injectives. So by the theorem, there are enough internal injectives as well. Our proposition, we had a proposition saying that we can compute X in HoTT via injective resolutions. And in a model, this means we can compute Xn via internal injective resolutions. And by the theorem, this is telling us we can always do that. And the corollary is then that the functor that I've written here is the nth right-derived functor of the internal HOM. That is, it recovers what's classically called sheaf X of R modules. OK, so we can always compute our X in these models via injective resolutions. We could even define it via these injective resolutions. But I want to give you an example of a computation using internal projectives. And it turns out this theorem, which is very nice for relating internal and external injectives, the corresponding theorem does not exist for projectives. Let's see that now. So we're still working with a site C and a sheaf of rings R on C. And I want to show you here that internal and external projectivity differ in general. So this definition, you could probably guess it. An R module P is externally projective if the external Hom preserves epis, and it's internally projective if the internal Hom preserves epimorphisms. Now, I'll give you an example of an internal projective that is not externally projective. So we continue in this category of CG modules, which were the Z modules in the topos of G sets, or the abelian groups in the topos of G sets. Then we've already seen an internal projective, and that's Z with a trivial action. The way to see this is that it represents the identity functor from mod Z to mod Z. So it's internally projective, certainly preserves epis. But we also saw an epi that doesn't split into it. So that means it's not externally projective. For the converse direction, that's a bit more involved, there's an example due to Trimble for objects he fixes a site, and he proves it that this implication doesn't hold for objects. You can update it to a statement about R modules. But it's a bit involved, so I won't give that here. OK, so now I want to compute a non-trivial x2 over the integers in the Sierpinski topos via an internal projective resolution. So we consider the pre-sheaf topos on the walking arrow, which is one way of presenting the Sierpinski topos. Then we have the following internal projective resolution of abelian groups or Z modules in this topos. So on the right here, I have the object the module or abelian group that I'm resolving. And I'm taking an internal projective cover. And then there's a kernel here, which I haven't written out. And this is the cover of that kernel. And it turns out the second kernel, which is this guy, is itself internally projective. So we have a resolution complete. It terminates in 2 steps. And so this object here should represent a non-trivial element in this x2 here. And in fact, let me write that out a bit more concretely. So extension of this guy by this guy, I'm saying it's non-trivial because this guy element represents an element in it, but you can actually prove that it's computed, that it turns out to be the guy you started out by resolving. That's kind of curious. But it tells you, well, this sort of shows you that our X groups are internal. This is a sheaf itself. So it's not an abelian group, it's a sheaf over the Sierpinski topos. And in fact, this computation generalizes. And we obtain the following theorem. The Sierpinski topos equipped with the sheaf of rings Z has internal global dimension 2, by which I mean x then vanishes for n greater than 2, and x2 is non-zero. I see that I've spoken pretty fast, but that means there's time for clarifications and questions. So I want to thank you for listening, and I'll accept any questions. Thank you.
Thanks a lot, Jarl, for this great talk. Let's give you a round of applause. And there was already a question in the chat.
Yeah, sorry, I didn't. I wasn't looking at
Jonas. No, that's okay. I think now is the right moment.
Yeah.
Jonas, do you want to ask your question in person? Otherwise, I'll read it out. Okay, I'll read the question by Jonas out.
Thank you.
He's asking, isn't the type of short exact sequences from A to B to B classically essentially small, since the underlying set of E is always in bijection with A times B? So,
that's a really good question. Yeah.
Maybe we can have Jonas to the discussion, just because he's asking how to switch on his mic. I think, Jonas, you have to raise your hand, and then I can activate you somehow. If you can just raise your hand, Jonas, or maybe try to
Well, I understand the question, and it's something we've thought about.
Okay.
So it's a good question. So I don't see the chat, so I'll just answer it. So first of all, this only works. Well, okay, yeah, okay. This turns out to not be true. So we have actually examples. We think in the Sierpinski topos where it's not true that if you have a short exact sequence, then the product of the two endpoints is equivalent as a type to the middle guy. This no longer holds. I think that's my answer.
Okay. Jonas is joining, hopefully.
Okay.
And, maybe we can
my problem is I have a small screen, so I don't really see what's going on. Okay.
Yeah, so Jonas is here, but also kind of not here with us, kind of Schrödinger's Jonas. Anyway, so while Jonas is maybe still joining, are there any other questions that you might have? Okay. No, if there are no further questions, then thanks again to Jarl for the great talk. And maybe it's easier for Jonas to ask a question in the discussion, in the discussion room that you can join now. I think Malena has already posted a link to the discussion room.
Okay, I'll join that.
So yeah, please, Jonas, if you can still hear us, please continue the discussion in the discussion room. Thanks again, Jarl. And we have a small break before the next talk of about 7 minutes.
Yep.